Okay, so hi and welcome back to this part 2 of our introduction to the channel. I just wanted to go over a couple more things that I missed in the first part of this. Mainly the first section was just sort of introduce what the purpose and focus and function of this whole project is supposed to be, and how I plan to go about things. And in this video, I just wanted to go into a little bit more the primary objective of our generalizable intelligence, the G part in the AGI as part of the AI. And the reason being, I sort of glossed over it in the first part because I recognize that it's sort of a lofty goal, and more important to me is the approach that we're going to take by going through a render engine like Blender to figure out other ways of visualizing the data that we're going to be processing through our neural networks and through our other models, SVMs and stuff. But I also wanted to outline very clearly where I was coming from with this project, my intentions, my latent biases, and things like that. And I know I kind of went off on a bit of a tangent about critical thought, but again, that is a huge purpose and point of this channel, is to sort of empower people to also take on this type of research and contribute to society in independent ways. So you'll forgive me for my voice. I'm going to be starting school again in a little bit, so I've been hashing out a bunch of these recordings back to back, and my voice is kind of taking its toll, but we'll power through. So ultimately, that is the end goal and purpose of the channel. So don't get me wrong. It's to empower others to show them that they're able and capable of doing this type of research and chasing exploration and discovery of higher knowledge and contributing to science just in general, because the field shouldn't be a closed-off, gated community, as I said before. So in this video, though, I wanted to talk more about project specifics and the implementation details of how I plan to go about this research project with objective number 1 in mind, which is the generalizable intelligence, the holy grail of machine learning at present. I guess the best way to describe how we're going to be tackling this is through modularity. And I say that sort of coming from a Linux background, but I've only been in the Linux community for a few years. It's not like a lifetime thing, although I wish I had done it a lot sooner. But essentially the philosophy of Linux is to have every program and application and every type of little process running in the background serve its own function and just do that function and do it well. So the idea is to have, even if you need like 100,000 different small little programs to have a system like a desktop up and running and working, the point is that you have something that you fix and meticulously curate so that it runs perfectly and smoothly, and that it's segregated from everything else and it doesn't affect everything else tangentially, right? Whereas with other operating systems like Windows or Mac OS, if one type of like an encoding algorithm or something that it runs in the background to do like its safety checks or checking for update, the worst is like Windows Update. as a prime example everybody should be familiar with, and it can interfere with everything else because it's tied in with all its little tendrils spreading into the registry and spreading into your file folders and using your network connection in the background. When you want to use all the bandwidth for yourself, it just won't let you because everything else is demanding resources for its own personal gain. All these other programs in other operating systems sort of work on like a greedy algorithm where they just take what they need. They might check to see if a resource is busy or not, but they don't really ask. They just take what they need. So the Linux operating system, on the other hand, instead of having one king or queen leader that governs and dictates all the other little underlings, every little piece of software that runs on your computer is very specific and tailored to one function, right? So, for example, your video encoders, you don't need a specific program just to get the encoder. You can just get the encoder, and any video program that you have should be able to use that encoder, that codec. So you don't need like 6 implementations of the exact same thing. You only need the one implementation, and then the software that uses whatever implementation that you have running. And that gives you the modularity in your system to pick and choose which type of audio controller you want to use. You're not stuck with the one that the operating system thinks it'll work best with, or the only one that it's optimized for. You can run whichever one you want, and you can switch between them because the piece of code that you're running only does this one function. So taking it out of the equation doesn't break anything else. There may be other things that depend on it, but you can use a substitute, or like you can pick and choose which components and which building blocks you put together. So I liken it kind of like Lego, how you have maybe the same block, same size block, and they all fit together, but you can have different color blocks. So maybe you want to build a house that's all red. You can choose with Linux to only use red blocks, even though there are others to choose from. Whereas with other operating systems, you have to use the ones that they tell you to use. It's basically like the instructions not giving you enough pieces to build the thing you're trying to build unless you build it their way. So that modularity is sort of how I wanted to build and structure these machine learning algorithms, because that alone, just in approaching it from that direction, by it, I mean generalizable artificial intelligence, it makes an intractable problem more tractable just from the onset. Instead of needing, billions and billions, Carl Sagan's invocation there, instead of needing billions of parameters to feed a model just so that it can learn a language, right? Well, humans have hundreds of other languages, maybe thousands, I'm not even sure. And you're never going to get anywhere if you need, 2 or 3 billion or 10 billion or 100 billion parameters for every different language that you want to train your text model on. I mean, sort of a bad example, because in this case, a lot of the syntactical similarities between languages actually translate, so you don't technically need to start from scratch every time you try and teach GPT a new language, presumably. I'm not actually sure, but irrelevant. The point is, instead of training one giant model all in one giant chunk with one giant piece of training data and one giant supervisor or hypervisor or whatever, it's training in small bits and pieces. Rather than having one model with 15 layers, and then the layers are exponentially more complex because you have to cross-multiply with every node to every other node on every other layer, then process every activation and cost function for every one of those nodes on every other layer, and then it expands exponentially as the layers get deeper and deeper in the neural network, right? So deep learning becomes intractable really quickly that way. And a lot of the optimizations we're looking for in that field of research is mostly mathematical optimization. So like using a fast Fourier transform instead of a Fourier, or using discrete values instead of like infinitesimals and yada, 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 right? Like we're limiting a lot of even our floating points on our normalization functions. We're limiting them to 64-bit or 32-bit. We're re-encoding matrices from 32 by 32 down to 16, and then we're upscaling them after the fact, and all these other types of little tweaks, and they're awesome for optimization, don't get me wrong. I'm going to use a bunch of them, but from the onset, I think we're operating on a flawed premise of trying to cram every training detail into the same model as we're training it. And I think that that's probably not the best approach, just based on, first of all, neurobiology. Our brains work in segregated localities, right? And it's not that they're restricted and limited to their own locality. Like, you can find an emotional sensor in your visual cortex, and that's why visual stimuli can give us direct emotion. So it's not that they can't interoperate or translate between one function to another, but the issue is by segregating modularly, you can reduce the impact of certain signals being transferred needlessly. So instead of processing the exponential growth of the depth of a neural network just through brute force, I'm hypothesizing that we could build modules of trained sets on very specific tasks, and then build models of those modules of specific tests and tasks. So for an example you might use for image detection, you might have to take a full-sized image and then downscale it to something a little bit more reasonable to be processed before it gets processed, to say 16 by 16. And then you convert that into a one-dimensional vector. So you take a two-dimensional matrix into a one-dimensional matrix. And then after you've done your processing on each element of that matrix, then you rescale it to 16, then rescale it back up to whatever it was originally. And then you produce an output from that field. We're still going to do that, but a better method is to take that approach one step further and actually apply the functions modularly like that. So I'm going to apply that set of implementation detail to a smaller set of very restrictive functions, such as processing a wavelength for a color stimuli, or processing a motion stimuli, or a memory stimuli, right? I might have another section of neurons that are even more fundamental, like more intrinsic, that manage memory, because even with human memory and, well, brain memory in general, biological memory, forgetting is more important than actually remembering, because what we're doing is we're culling the useless information to make room for more new connections that actually matter and that are pragmatic and useful in our day-to-day. And that's how we functionally develop without making our brains just never stop growing, right? We'd have giant balloons for heads if we just never forgot anything. So the selection process of forgetting is more valuable to having recollection and memory than is actually processing new, or not just processing, but growing new connections between neurons, if that makes any sense. So for another example, you might think of like the difference between muscle memory and things like, what do you call it? Instinct. You might think of it as the difference between a muscle memory and an instinct. You can train a muscle memory through repetition, and constant repetition means that neural connector is going to be constantly reinforced. So there's the old adage of neurons that fire together wire together, right? The more you stimulate one connection with another, the more you feel a sensation on your fingertips with the same firing as the motion of your hand reaching out towards something that you see. Your visual sensor of seeing your hand touching an object will connect with the sensory perception of your fingers touching that object, and it'll wire together with the motor sensory neurons of the volition of motion towards touching an object, for example, right? So when those things wire together, your brain becomes automatic in its response to expecting a sensation of touch when it sees your hand touching something else. And this is sort of evidenced by just simple tests where you put up a block so a person can't see their own hand on the other side, but they see like a rubber hand, and you touch their real hand at the same time as you touch the rubber hand, and before long, the brain of the subject in question believes that the rubber hand is their hand. They're staring at it, they know full well that it's not their hand, that it's a rubber hand, that their vision's being blocked, but seeing that rubber hand get poked at the same time as their hand under the table is getting poked in the same spot will wire the brain to think that that object is their hand without much effort. And that's sort of the process I want to take with these neural networks in the architecture and for the model that I'm developing, because I don't think it's necessary to have 6 billion parameters to have a complex model. It might require that we have 1,000 different pre-trained models, but each one of those models could be trained in, say, a few minutes or an hour, as opposed to GPT-3, which took months and months and like tens of thousands of watts worth of energy just to get a language model put together through symbolic representations of all the training data and categorical representations that it was fed through its training process, right? And then there's all the fine-tuning, and there's the risk of overfitting and going back to the drawing board and figuring out all the complex math, and all of that just seems like complete overkill to me. I think it's absolutely important that we do it, because research is research, and it's definitely going to teach us a lot, and it's awesome, cool model, fun to play with and all that. But practically speaking, if we're working towards a generalizable artificial intelligence, I would hypothesize or conjecture that it makes more sense to apply the same type of reasoning of modularity in building our machine learning models than it does to do all that other stuff in the hardest possible way. So the approach to this research project is specific to the Linux philosophy of building modules that function like all the time, really well, reliably, no questions asked, as opposed to models that, work 90% of the time in most cases, but sometimes classify a cat as a fish. Well, a cat model has all these different types of stimuli that it's processing. It's looking for fur, it's looking for face shapes, it's looking for nose to eye ratio, because cats have small head, big eyes, and little noses. And then there's always going to be the dogs that look like cats, or there's going to be a cat-shaped cookie, right? That a neural network could easily misinterpret as a cat because it's going to rely heavily on its edge detection, right? Whereas if we have models of just strictly purely edge detection in all these different cases, those can be generated with an AI with very little effort. You can find those edge cases in very well-trained, sophisticated models and use that as training data for these simple models. And you can do that without even having to downscale and upscale a lot of the time. Or you can downscale to a higher resolution than you otherwise would, and then there's less loss and there's less error rate, right? So in keeping with that, when you have something similar to an edge detection and, like, say, an audio noise detection, if you apply those two things together, you should be able to then afterwards take those two pre-trained models and stick them in, plug in a video input for a sequential new training set, and be able to train object detection on a moving object in, like, cloudy or foggy conditions where there's visual noise, right? Because to a computer, there's no difference between signal noise from audio and signal noise from a video feed. They're both just digits and a spasticity of color variation which don't comply or fit with a perfect representation of physical reality, right? So volumetrics can easily be processed through or simulated through Blender, which is the 3D modeling software I'll be using. And using those volumetrics, we can dynamically produce, using noise texture generators and things, we can produce the training data for that type of visual noise and train it against our object detection and noise detection models that are pre-trained on other sets. So using a bunch of pre-trained, highly sophisticated open source models, we can also use those as generators or as supervisors to learning our more simplistic, very straightforward models. Because the more data we have, the more accurate our models are going to be, the better outcomes, the more reliable our modules will be. And then once we have very strictly reliable modules, we can then allow for an error rate after the fact, like the way our brains do. So when we see a baseball player hitting a baseball, we see him swing, and then we hear the crack of the bat come after. If you're within, I can't remember the distance, but if you're within like 100 feet or something of them, your brain's going to process the crack of the bat and the visual cue of the bat swinging and hitting the ball, and it's going to offset the time for you and readjust it in your head. But as soon as you get to about like 100 milliseconds difference, all of a sudden there's a coherence drop, and the sound and the visual stimuli become separate events in your brain. And the brain is the one compositing those suborder processes. The brain isn't actually seeing things as they happen. There's always a time delay between when the stimuli came in, when it was processed, and then the interpretation of our conscious awareness of that event after the fact. So I intend to build a neural network model based on these fundamental modules, not so that they're perfect and infallible. We're going to introduce fallibility to them afterwards, because illusions and things like that are what give us imagination and creativity. And when everything's too perfect, you can't make proper music, for example, because we're just not in tune to feel a harmony with something that's a perfect relationship with timing and cadence and rhythm and all that. There needs to be some subtle variation to it, some imperfection, some humanity to make it really come alive and feel inspired. And an easy example of this is if you plug in like Beethoven or Mozart or something into a computer and you have it play like the notes on cue, the perfect notes, the perfect tones and everything, and you said it sounds mechanical. It doesn't come across as music. But when you play the same symphony from two different conductors, you can hear the subtle variety and the vibrancy of just like the timing, and the crescendos are different, the amplitudes are different, the forces are different behind them, because humans are intrinsically imperfect. So even though we become masters at our craft and our trade, it's our imperfections that make beauty from that mastery of the craft and the trade. So you want that fallibility embedded into the model for certain, but first and foremost, you want the module to be as perfect as it can be at the most limited function as it can be, and you can introduce that variety and variability to it after the fact, rather than trying to fine-tune a billion parameters all at the same time and feed it enough data that it can actually produce something useful or meet an objective or a goal, or have even a consistent cost function associated to the outputs that it generates. It makes a lot more sense to just fine-tune and tweak the creativity of the model in a general sense from the compositional state, as opposed to from the functional stimulus state. So that's sort of how we're going to be approaching things. And I just put this up here because I've been using some terms, and I really should at some point start describing them, and I guess that figures under the theory of this project, and I'm going to be putting all the theory videos under the project header there, so might as well start with that. This will be a half introduction, but also a half step one. So one of the terms I keep using is dimensionality and encoding and translation and things like that. So I'll put like trigonometric functions and all the mathy stuff under the math subheader, so that it's a lot of people might want to avoid that specifically, but that's also going to be for my research paper the most pertinent to the research, so it should be classified on its own. But through the theory, we'll do a little bit of math and a little bit of code and all that, just to be able to relate all the different pieces between the tools we're using, the software we're using, and the theoretical practice and implementation details of the architecture that we're designing and engineering from start to finish. So I guess the first thing I want to talk about then is, or mention on here, is encoding. Let's see if I can learn to write while I'm on recording. So what I mean by encoding is, like, if I'm going to do a picture, like, say this. If I'm going to try to take a higher dimensional picture of, like, say 1600 by 1600 pixels, I don't want to process each individual pixel, because as soon as I have one extra layer, that's going to compound the complexity of the compute requirements and resource requirements needed to allocate towards that single thread of operations. And if I'm running that thread across an entire vector of other potential outcomes or inputs, or I'm comparing it against a bunch of other inputs, then it's really going to become, it's going to get out of hand really fast, the amount of compute power we need. So when we encode something like this, we'll take this, like, small section. Oh, I guess there's nothing up there. I'll put a little sun here. There we go. So we'll take this small section like this, and I'll commonly refer this to as encoding, or this is also like a kernel. It's also referred to as a map. But this whole thing here is nothing more than a matrix of numbers x and y, right? So that'll be x1, x2, y2, x3, y3, etc. And that'll be the location details of the pixel. And then from each one of these, I'm also going to have an RGB, like color values, right? And these will be from 0 to 255, which gives us our color space of, what? Oh, geez, that's embarrassing. Is it 16 by 16? Yeah. So 256, but 0 counts as our first index, so 255. So that essentially means our color space, oops, get out of there. That essentially means that the color space is, okay, 16 by 16. So that's the same thing as that. So that means I've essentially got an X, Y, 1, 1, R, RGB, and then each one of these is 16 by 16. Or in other words, 16 by 16. So that's a vector, and this one's an array. So same thing, but arrays in programming are left to right, vectors in math are top to bottom. This little arrow on top of the V, that's to denote a vector. Not crazy important right now. But all of these encapsulate or encompass or comprise one single element in here. So going back to our kernel map here, we're going to have basically a section of an image that we're breaking this image down into a whole bunch of things. And remember, this is the encoding part that we're talking about here. We're going to take this section of the image and process it in little bits and chunks. We're going to break these chunks down, and then this little chunk might have like hundreds and hundreds of pixels in it, right? So if I only want sections of, let's say, I'll do a 3 by 3 section. Then what I'm going to do is I'm going to take all the pixels from all of these little sections and just sort of average them together. And the way we go about averaging them together can be a different formula. It doesn't have to be one standard way of doing it. And I just want to point that out. Like, I'm going to keep it really simple for this example, but don't think that it's like written in stone that it has to be done this way. This is absolutely completely variable and dependent on the type of operations that you're doing. But this similar process, whether we're using pictures or not, is going to apply to everything else anyway. And I'm going to be using a lot of encoders and transformers because I'm using a graphical model that's based on vectors and matrices and stuff. So that's the way I'm going to be able to re-implement their hardware optimizations most effectively, is if I use this type of machine learning model. So anyway, so let's say I take all of these pixels here, and if you'll notice from this section, that's this section down here, from my kernel is this one here that we're looking at. There's nothing in it, so it's mostly just going to be all zeros. So in this case, a blank square is 0, and a full square equals a 1. So that one's 0, this one's 1. That's sort of our legend. So most of these will all be zeros, right? But when I go up here, where I've got all this dark area, maybe I'll take this section next. And there's like this line that comes in here, and this part's all black, this part here. So the value output from here might wind up being, let's say we're using an average. The value output from this one might be 0.1 0.15 or something, right? Because most of it's blank, but there is some black in there. And then this one's going to be mostly black. So this one might average out to 0.91. And remember, I'm normalizing these, so the process of normalization, you take whatever number I'm using here, you just divide it by the maximum. And that's going to give us all values between 0 and 1. So everything's going to be a floating point between 0 and 1, and 1 is like 100%, 0 is 0%. So 0 means I've got no color or anything in here. 0.15 means this whole block has an average of 0.15 dark, and this whole block has an average of 0.91 dark. So you can see already where I'm building up a matrix out of a larger, higher dimensional matrix, and I'm re-encoding it through a kernel map so that I can get values, pixel values for whatever was filling inside of the different portions, and then I can recombine this one into, move this over here. So I can recombine this into a straight vector like this, just by building all those blocks together. And I can put all my values in here. So this is N1, N2, N3, and so on, till I fill out the whole kernel map. And then I can apply this process over and over and over again. I can do another kernel over here and give it some overlap with the last kernel. Another one over here, overlap with that kernel, and another one over here, overlap with that kernel. And then in the end, I'll have encoded myself several bars, basically, several vector channels of my re-encoded texture map, just based on the one image and changing the dimensionality for the original image, downscaling it to whatever this was. This one's a 3x3. So where do I put that? 3x3. Right? So now I'm downscaling from whatever these dimensions were over to a 3x3. Then I'm lining them up in a vector like this here, where this is just K1. So that's kernel number 1. And this will be K1, K2, K3, K4, and then K ... etc., right? So then after you've got all of these encoded into from a two-dimensional matrix, I re-encode all of this into a one-dimensional matrix, then you can apply transformations to these. You can say, you can flip them, so you can transpose the vectors like this, line them up this way, okay, one next to the other, K1, K2, K3, etc., right? And then you can repopulate by taking, say, a cross-section of all three of these kernels. And remember, they're overlapping with each other here, right? So if I've got 1, 2, 3, 1, 2, 3, 1, 2, 3 down here, I'm essentially able to take, just these two top ones in the bottom and do diagonals, or I can do other way diagonals, or I can do vertical cross sections, or I can scatter them, one here, one here, one here. You can sort of recombine them any way you want. And as many ways as you can think of recombining them, you can throw them together programmatically, and then you can call this, say, I want to use different. So that's a Z. So G of Z might be this. And then G of Z2 might be one that goes like this. And then G of Z3. You get the idea. So the point of re-encoding these, right, is you're looking for relationships through statistical reference. And when we're training it, we don't exactly know how it's going to find the best reference. So the easiest way to go about this programmatically is just say, I can determine this. I can say, hey, I want to downscale it from whatever input I get down to this, or I can downscale it by a fraction and say just always do it by down to 20% of the original size, or you can do it based on a hard limit, like no smaller than this, no larger than this, anywhere in between, keep it the original size. Like, you can set whatever rules you want, but once you've set the rule, you can automate the process of figuring out all the different possible permutations to examine. Without knowing ahead of time which you want to use, you can just do them all, process them all, run them concurrently in your GPU or from your CPUs, because that's the whole point of parallelism, right? Is that you can, you're not limited, you don't have to wait for GZ2 to finish to start GZ3, because they're all working from the same set of information. So you can plug all of that data into your GPU and then concurrently run as many permutations as physically possible from that scale size, from that kernel size, from that map size. And the way that these are helpful is that you can find patterns and correlations that you wouldn't otherwise necessarily detect. But a lot of these types of correlations we do detect, not just visually, but like our auditory sensors do the same thing too, with like octaves and harmonies and tempos, and we catch so much of this detail from music that we don't even realize just because we're attuned to it, just biologically and naturally, right? But a computer has no natural biological evolutionary, there's no natural selection for a computer deciphering the difference between music and random noise. Music might be a sign of like a cohesive group, and it might bring us emotional comfort because we're social beings, and the more social we are, and the more emotionally sound we are, the better we work together, and the better we work together and cooperate, the more viable we were as a species, right? So it all tended towards evolutionary processes to have this type of awareness, or like subconscious awareness of things like music or art or dance or interpretation or subtleties of language or different ways of physical contact or fighting and arguing and everything like that. Is as complex social creatures we've developed over time because of some evolutionary benefit along the line that suited us towards reproduction and being fit for survival during the hardest times, and others not so much. And it doesn't mean that everything that survives was always the best thing. Like, our feet and spinal columns are terrible adaptations, but they worked well enough that we didn't have to evolve much from them. But everybody has back pain at some point in their lives, and everybody's feet hurt at some point in their lives, and it's because our bodies aren't, perfectly adapted. They adapted as well as they had to, basically. So a lot of the things that we do evolve aren't necessarily the greatest benefit, but when we're structuring evolution through a computational sense, we actually have the opportunity to engineer the greatest benefit. And the best way to do that is to try out every possible permutation and see which ones are most viable. Now, it may not be readily apparent that one set of G values here are G functions, G of Zs. It might not be obvious that this one's even useful until 3 or 4 layers on, right? Like, color wasn't necessarily useful at all until we started picking different varieties of fruit and had to test for their ripeness. It would be really hard to test to see if berries are ripe and full of nutrition if we couldn't see the color red. Things like that. So it's like with our motion detection sensors in our eyes, our optic nerves. Those are black and white sensors, and our color sensors are more emotional stimuli. They're more lending to our abstractions and surreal feelings, whereas our amygdala is pretty much the thing that gets triggered by motion. We're just like immediately draw our attention to things with motion. And that's why our eyes can never actually sit steady. they're constantly jittering back and forth because they're looking for some type of motion. And that's to spot predators in bushes, prey that moves or rustles, because most prey have adapted some sort of camouflage just as their fitness for survival. But yeah, so the point to all of this basically is to say, like, we're trying not to prejudge a model for its utility until after several models down the road. So we're going to programmatically build a whole bunch of really primitive, simple sensory perception models, basically. So one will be, let me just hide this here. So one sensory perception model, sensory perception primitives. So one of them that I talked about already is going to be like edge detection, right? So if I've got an image with a whole bunch of complex shapes, my stickman's not exactly a complex shape, but I might have, like, model 1 might just do lines like this. And the way it does that is by having a matrix that looks for ones along the horizontal column, and that's it. It can't look for ones along every horizontal column, because then it would just be looking for an entire dark block. So all it can do is this column right here. But M11, like sub 1, or I'll call it A, M1A might be 111 across the top. Zero, 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 zero. And M1B, obviously, might be across the bottom. So 0, 0, 0, 0, 0, 0. You know, same thing. But combined, these three constitute one edge detection algorithm. But only in the horizontal. And again, this model might only be useful for images, right? Because we're going to use this as part of our kernel across our picture. So if this is my picture frame here, and this is my kernel that I'm processing, this is the next kernel that I'm processing, and this is the next kernel that I'm processing, something like that, right? I might take this one here and then put my edge detector through it, and all you have to do is multiply, well, like this will be this one here, so. All you have to do is multiply this matrix with the pixel values that you're covering from this other matrix and see if it returns a 0 or a 1, because anything multiplied by 0 returns a 0, and anything multiplied by 1 turns itself. So if the output of this one, if I have a diagonal that runs across this way, right, I might get 0, 1, 0, 0, 0, 0, 0, 0, 0, right? Because I'm only getting this one little angle coming across from here, and that's a 0, that's a 0, that's a 0, 0, 0, 0, 0, 0, right? But if I catch this right across the arm here on this other one, put this one down here, when I multiply one matrix with the other, when I cross them over, when I apply that map to my frame of reference, what I'm going to wind up doing is getting ones across the middle, right? Or maybe slightly less, because like if the color values, remember over here, if the color value winds up being between 0 and 255, and then I normalize it to, my max is 255, so I normalize it. Maybe it winds up being like 0.91 here, right? So when I go back to here, I might get a 0.91, and then a 0.89, something like that. But the output value is going to be much greater than 0. That's the whole point. And anytime I get something greater than 0, this is going to spit out as my output from my model. It's going to say, hey, I got an 89% chance that this is matching my directive. And my directive is horizontal line. And when I run M1B and M1 through these, if I find the same match from the kernel up here with this M1B, then this one is going to be outputting the same type of deal here with my 3x3 matrix, 0.91, 0.89, and oops, it's a bit messy. I should say too messy. 0.91, my 0.89, and then my 1. And this is M1B. That's when my horizontal line's at the bottom of my kernel. M1A was when my horizontal line was at the top, and M1 was when my horizontal line was in the middle. So when all three of these combine, and they all say, hey, I found a value greater than 0, I'm 89% sure, I've got a horizontal line at some point in this picture, then you can reference this frame, and the other frame, their indexes together, and you can say with a high degree of certainty that there's an edge here. There's a contrast between the space below or above it, or left or right of it is the same. It's both saying the same thing. In a horizontal line, I'm saying there's a similarity from the left of my center and the right of my center, and there's a very high dissimilarity everywhere else. And in this case, it's going to say there's a dissimilarity here, but left and right of my center, there's a high degree of similarity. And when you combine these together, when you composite these types of kernels together into a single frame reference, you can then say with a high degree of certainty that I've got a horizontal line at this spot in my picture of 89% certainty, or whatever the statistical output is. And when you've processed this for every possible permutation and covered the entire image in several iterations, and that's something you can do in parallel, because one frame of reference has no impact or bearing on the computational output of the next subsequent frames, which makes the processing power required for computing these types of models vastly inferior, or less, it's less demanding, it's less taxing computationally than if you have a large model with sequential time series data, which is dependent on previous processes, and which also has a huge number of parameters. In this case, the parameters would be the size of the frames I'm using here. Like if I had a giant kernel space of like 600, and I had to run 600 permutations per version of this M1, and I had several versions of this this map that I'm iterating over this entire image through, you could see it compounds as the complexity grows, right? So the number of parameters dramatically increases the amount of processing power and compute requirements, because every single one of these frames needs to be computed. And every single one of these frames has several individual blocks that need to be accounted for. And then every time you do one of these frames with all of these blocks in it, you have to do it several different ways in several different times. And you're going to do it on several different input images. And then you're going to cross-reference all the image data with all the kernel data with all the mapping data, or the encoding data, and then you're going to have to translate it back with outputs and then compare all the outputs and say this one's 89%, this one's 67%, this one's 73%, and then this vast number of them is all going to be 0. So the more different models that you have, you can train these individually very, very quickly, and you're not losing nearly as much when you re-encode them or downscale them to a smaller resolution and then upscale them again after the fact. You're not losing nearly as much information as when you're processing like a symbolic text model that's going to have references and pronouns for subjects from the same sentence or from a sentence prior, where you have to keep in a memory space the subject and context and verb tense and all that type of complexity that's in language. You don't have to keep all of that in mind at the same time. With this type of substructure of model, you're basically building subroutines or individual Lego blocks, which you can then build into more complex structures afterwards. So that's what we're getting to with encoding. This is how I intend to approach our AGI model, and this is how we're going to be training it in Blender using graphics hardware and multi-core processing and texture maps and rendering and vertex groups and boundary conditions and all of that fun stuff with the built-in optimizations for physics simulations and 3D object modeling through Blender. And the way we're going to go about that through Python is by setting up a Python environment, which Blender is going to use when it launches. And I'm going to install all of my third-party libraries like TensorFlow or PyTorch and NumPy and all that into the environment that I create, so that when I launch Blender, its Python interpreter already has those modules installed and ready to be imported. So we're kind of jimmy-hatting things together, like a MacGyver type of approach to machine learning. But hopefully, the statistical representations we get from the outputs, we can also then map to 3D objects in 3D space, or even 4D if we want to animate them with time or whatever. But I mean, my computer would render video sequences so much slower, it wouldn't even be worthwhile. But if you just build objects, then different shapes can represent different parts of a model or compositions of a model. Different colors can represent different dimensions of the data. So if you do 3 passes like we did here for a horizontal, I could represent visualized data as just colorizing these through a diffusion map within Blender, so I could visually see which ones are more accurate, or which ones overlap the most, or which ones are least accurate, and maybe put less of a weight on the outputs of the ones that are least accurate. But if they're still providing some sort of confirmation data, then you don't want to discard the data entirely, because it's still pertinent, it's still useful. It's just less useful than the other 2 varieties, right? So there's all sorts of little tweaks that you can do by repurposing the material nodes within Blender, or by using functional non-destructive modifiers and applying those to the objects we create programmatically in Blender through the Python scripts. So there's all kinds of different ways that we can not only process the data, but also make use of the optimizations built into Blender and the libraries that we're building. But there's ways to make use of those and re-implement them to visualize the data that we've also just finished processing, so we can see which parts of our training are most effective, or how the training is building out our model, how the model's been constructed, basically. And if you really wanted to, you could render time lapses of all this too, and render that into a video after the fact. You can add audio data to it, you can track it, you can interpolate from one shape to another, or from one color to another, or from one texture to another. So there's all types of variations that we can use to actually visualize the implementation details of our trained models, in addition to training them through optimized hardware. And the benefit to that is we're removing the black box aspect of deep learning neural networks and making it more legible. So it's going to be much more effective for all of research going forward if we have a better way of visualizing the black box details of deep neural nets, because that's the only way to know for sure before we apply these types of models and put them out into the wild, say for like traffic signals, or for operating airplanes, or for handling financial systems, or rerouting our emergency service vehicles, or regulating markets, fact-checking politicians. Like, an AGI would be so much benefit to so many people if it was open source and reliable to everybody equally, right? And the best way to do that is to have the implementation details not be hidden behind so many layers of abstraction that we don't even know how it figured out its output. If we can trace back the development of the output, then when it does make an error, we can correct the error so it doesn't recur. Whereas now, even if we find an algorithm that's 99% effective, the one time a car turns because of a shadow on the road and hits somebody and kills them for absolutely no reason, I mean, that's a tragedy. If that's avoidable, we need some way of visualizing our data, or at least figuring out traces back to the origin of how it made a decision or why it made a decision before we implement these types of algorithms into civil society for all to enjoy the benefits. With that, I'll just maybe list off a few ways that this type of thing actually benefits everybody. And I think the biggest way is probably through just like social governments and organization. We waste so much energy, and there's so much conflict that's based on absolutely nothing but personal biases and made-up fantasies and religious fervor and zealotry and bigotry and all these nonsensical ideas of like supremacy or inheritance or entitlement. They go out the window when everybody has access to a logical system that can tell them exactly why their beliefs are false before they go out and act, or before they go out and like double down on a stupid idea because of their ego or whatever. If people at least had access to not just like a home assistant that sells their personal data so that they could be marketed to, but a home assistant that can help them vote better, not by telling them who to vote for, but by telling them the information that their opinions are based on might be flawed by which percentage in this specific way, the person can still figure out for themselves whether or not they want to believe it, whether or not they want to follow a religion, but at least they'll have or a politician, but at least they'll have somebody raising a flag in the privacy of their own home where they're not embarrassed or called out as bigots or made to look like fools in front of people, which stimulates them to emotionally respond by doubling down and reinforcing a cognitive bias. If you give them the opportunity to at least better themselves and be educated about the decisions and choices they make that affect everybody, then they're less prone to do really radical behaviors, you know what I mean? And to me, that would eliminate so much of our crime, because, like, first of all, you would have some type of system that would not just say, oh, don't worry, you can be anything you want if you just gotta buck it up and work hard enough. If you had a system that actually rewarded hard work, a meritocratic system that was fundamentally opportunistic, then anybody could just decide to better themselves, and they wouldn't have this, or they wouldn't be as prone to feeling completely trapped and resorting to criminal behavior to get out of a bad situation. Because as we know, psychologically, most criminals believe that all the crimes they commit are ones of necessity, or they're crimes that they were forced into by happenstance beyond their control, or they already made a bad decision and there's no point and they've already given up. Like, these irrational, illogical trains of thought or modes of thinking are what cause a lot of the discord in our civil society, and those things spread out to everywhere else. They spread. So it's not just one person's life that's screwed up when they decide to start selling drugs and get caught and go to jail. It's their kids, and then their kids grow up with other, dissimilar but maybe similar false beliefs, which then in turn creates other issues for them going down the road and then for their kids. But it's also on the person left behind who has to raise the kids. Now they're a single income household, and because everybody's voting irrationally, their savings don't go anywhere, so there's no way for them to build themselves out of a hard situation, basically. Like, we're reinforcing all the worst behaviors in civilized society strictly because of our irrational thinking. From the idea that because we're rich, we must have earned it, like the Donald Trumps of the world, or basically half of white America believes that they had no privilege. And on the other hand, as a white man, I know for certain, having physical disabilities, that I certainly didn't get the privilege of a white man, because a disabled person has there's a negative compensation for that type of natural born privilege. But also, being born and raised in a country as liberal and social as socialistic as Canada, it's less pronounced in this environment as it would be in another country. So there's all types of little details that go unlooked or unnoticed or unresponded to when statistical analysis isn't factored in. Like the idea that every white man is better off than every black woman is preposterous, because if you look at the weights applied to having money, a rich black woman is like multitude more powerful and has more influence and a more comfortable life and longevity and access to healthcare than a poor white man does. So it's not as simplistic as saying any single factor creates a privilege that somebody else must pay for. That's so absurd and asinine. It's only going to breed and harbor more resentment from the disenfranchised white men who were poor and, you know, who saw opportunities taken from them to help others around them when they themselves got no help and needed it. And this is just one example. It's not a defense of like white nationalism or anything like that, obviously. The point is it's a statistical analysis that's rational, and that needs to be factored into all of these social situations and considerations, politically speaking, when we're imposing legislation and policy for things like affirmative action or for grants or student vouchers or for what do you call it, like the housing subsidies for affordable housing. Things like setting mortgage rates or like opportunities in the market. Accredited investors get, you know, the people in least need of access to funding to better their lives get the cheapest access to funding. And they also are the only ones who make money in percentages as opposed to trading hours of their life for fixed amounts of dollars. So like the way the system is implemented, because of an irrational belief system that people are electing into office and voting into office based on other manipulations of belief systems, a lot of that could be wiped clear by simply having a rational, trustworthy, open source, verifiable and traceable neural network model that can not only extrapolate from the inputs given, but interpolate its extractions. Yeah. That's just as important, because if you can't interpolate where it's getting it from, you might as well be asking Google what you should do to regulate Google, right? Because Google's assistant will tell you every time that, you know, they don't censor anything on YouTube that doesn't need to be censored, and they're all in favor of content creators and copyrights and fair value and all that BS. And then you see what they do with like Business Casual and RT America, who I just saw the other day is finally suing YouTube over it. And the frivolous copyright claims on my channel is a perfect example. Google's got the greatest AI system in the entire, probably in the world, and they can't figure out that I'm using the same licensed intro music to every single video. Somehow. They want copyright claims just so that if I don't dispute it, they can demonetize and throw ads and they get free content, basically. And I'm not even here making money. It's the principle that bothers me. It's the principle that they're trying to screw creators out on the basis of some copyright infringement they know full well is bullshit. That to me is just annoying. It's irritating because I know they know better, they know better, and they're playing dumb. So things like that we need to regulate properly, and our legislators don't know the first thing about the internet. Never mind streaming or encoders or, you know, anything. Social media, you name it. So they're the worst people possible to put in charge of governance of that type of thing. It's the same with the financial markets. People who don't know economics shouldn't be making economic policy. They shouldn't be drafting trade agreements. They don't know what they're doing, flat out. And the evidence of this is they clearly don't know what they're doing. If OPEC's mandate is to stabilize prices, just look at a chart of OPEC for the last 20 years. You might as well have not had one. It's literally gone from 0 to 130. Like, that's as volatile as the word volatile can possibly mean. It's going from 0 to a maximum, to the highest it's ever been in the last 10 years. So clearly that legislated cartel isn't serving its mandate. It's the same with like the drug enforcement, where they lock up addicts, but they won't give them health care, even though the scientists of our country have measurably and overwhelmingly concurred that addiction is a health problem and not a crime problem. But instead of jailing the bosses who are shipping the drugs into the country, who are selling it to all the small dealers, they lock up all of the users. It's just that type of insanity needs to stop. And I think rational systems that can help in any regard should all be welcomed, but we need to make sure that they're open sourced and that that we can audit them, so that when they do make mistakes, we can correct them, we can point out the failures, we can all talk about them together. We need to be able to edit them ourselves so that we can influence our own influencers and not have other people influence them for us. They need to not be operating in the background. We need to be able to trust that they're not on and listening and being used to manipulate us later on just because they're overhearing what we do. Like, all sorts of things like that are solved through open source and debate and discussion. And this type of project and artificial general intelligence not only helps with organizing resource management and supply chain management and equitable access to markets and meritocratic initiatives, but it also helps us it helps us discern adequate, or come up with adequate, appropriate responses would be the better word, appropriate responses to the situations at hand. So the advice we get, whether to save or borrow for our business, should be one that's rational and not one that's been sent to us from a bank or from a government who wants to look good by having bigger numbers, future be damned, right? Because they're only looking forward to the next election and trying to get reelected as their only job. It has nothing to do with governance. That type of thinking and market manipulation and intentional misrepresentation of statistical analysis needs to stop. Otherwise, we're not going to get better. We're just going to keep going to war and keep destroying things in our free time just because that makes some people rich and because we believe it's in our best interest because we were told. If we were all more rational, we'd all live better lives, we'd all be richer from it, and we'd all have the opportunities we want. We'd have the opportunity to work less if we don't want to work as much, and we'd have the opportunity to work more if we have the ambition for greater things or for more toys or whatever it is. More holidays, more vacations. So we'd actually have the control and the freedom to run our real lives if we weren't spending so much money on padding the pockets of people who are least productive and contribute the least to society as a whole. So AGI is a step in the right direction. That's a huge motivating factor for the pursuit of this type of project, in addition to preserving being custodians of the planet and preserving the environment and all that, because resource management and managing like food scarcity and transportation, logistics, and all that kind of stuff, with a coordinated AGI would run supremely more effectively with the current infrastructure without any added investment required. We could simply manage the things we have better by at least 20 to 30%. If you deny that, then you must think that humans are already at the apex of our species and that we're somehow magically perfectly efficient in almost every way, except for one or two, which, leads us down to an only 5 or 10% loss. That, to me, can't seem even possible, considering we've only just discovered technology. Informational technologies we've only discovered within the last 100 years, so I don't think it's even feasibly responsible that we've discovered all the best use cases and implementations of the internet even. In the last 20 years, pop-up ads are a perfect example of this, but before I get into another belabored rant, I will end it there. AGI is the main focus and goal. Our approach is going to be to tackle it with a whole series of reliably small encoders that are traceable, and we're going to use all types of neural networks in a similar way. So we're going to use deep neural nets and backpropagation nets, but we're going to limit them to very distinct and finite functional use cases, so that even if there is some black box element to it, it's not so much that it ever distracts from the whole output that it produces. That's the goal. So hopefully you found this interesting, and hopefully the frivolous copyright claims of YouTube don't make this video take too long to come out, because it's already a bit late having to deal with all the other ones, and my videos are already out of order and I've only got like 4 of them up. But anyway, hopefully we get onto a rhythm soon, and that is that.